All right, in this video, we're going to talk about some application problems for the chain rule that we have been discussing in this section. I have my TI-84 calculator ready to show you over on the side. So this video is going to be in widescreen format. Most of the time I make them in a different ratio so that it's better if you're viewing them on a mobile device. So remember, if you're using your phone, to try and turn it sideways, or just view this one on the desktop so that you can see everything that's going on on the calculator as well as what's going on the whiteboard. All right, let's go ahead and get started here. Our first application here has to do with compound interest. It's problem number 69 from the textbook. And it says that you deposit $1,000 into an account with an annual interest rate R in decimal form, compounded monthly. At the end of 5 years, the balance A is given by the formula. And so they don't make you know the formula off the top of your head, but there's your $1,000 principal that you deposited. And it's 1 plus R over 12 to the 12t, where t is let's see, does it say, it says 1, doesn't it? At the end of 5 years. So 5 times 12 is 60, like that. So the only variable that's left here is R for us, and they want us to find the rate of change of A with respect to R. That would be dA dr. So dA dr is equal to 1,000 times 60, 1 plus R over 12 to the 60 minus 1 is 59, times the derivative of the inside with respect to R is 0 plus 1/12 will be 1/12. So let's clean that up a bit. I'll just call this 1/12. 12 goes into 60 5 times. 5 times 1,000 is 5,000. Times 1 plus R over 12 to the 59th power. Now, I do not want to calculate this by hand, which is why I have my calculator ready. So I'm going to enter this right-hand side as a y equals equation. And I'm going to call that 5,000 times 1 plus, and instead of R, I'm going to use X over 12 raised to the 59th power. I'm going to use my table settings to make sure that my independent variable is set to ask. And then I'm going to go to my table, and I'm going to be ready to enter these different R values that they give me. So the first one they give me is the R is 8%. And they want me to find what my accumulated value will be. So for part A, when R is 8%, dA dr, my rate of change of my accumulated value with respect to R is going to be 7,399.90 dollars per whatever that is. So I guess I shouldn't put a unit on there, but the A is in dollars and R is in whatever it is. I'm not going to say percentage points because it's written as a decimal. So we'll just leave it as at that. me actually see if I can see what units they used. 69 here is per 1%. So if we are going to change this to percent to per percent, we're going to divide by 100 and say that this is approximately $74 per 1%. That's how the book answers the problem. Okay. So B is going to be R is equal to 0.10. So 0.10 gives me DADR is 8158.56, and that's going to be about $82 per 1% when we round to the nearest dollar per 1%. And part C asks us if R is 0.12, then DADR will be, and we're going to make this 0.12, that's 12%. And we have 899.355, but we're going to say that that's about $90 per 1%. Just check those answers here. 8159. So for some reason they made this go to 2 decimal places. That one, when they tried to round it to 2 decimal places, it rounded up. So let's just keep this the same, 89.94. There we go. Keep it consistent. All right. Let's move on to number 70. Even though this is an even number problem, we're going to do it as an example because it's one of the only ones of this type with this application. So the number capital N of bacteria in a culture after T days is modeled by capital N equals 400 times the quantity 1 minus 3 over T squared plus 2 to the second power in the denominator, close parentheses, and we want to find the rate of change of N with respect to T. So dN dt, we're going to have that constant multiplier 400 just sits there, times the derivative with respect to T of this, and I'm going to call this 3 times T squared plus 2 to the negative second to help me out. So dN dt is 400 times, and then when I take the derivative of what's inside here, this is 0 minus 3 times a negative 2 t squared plus 2 to the negative third times the derivative of the inside is 2t. So that makes this dn dt is 400 times negative 3 times negative 2 is a positive 6 times 2t. That makes it 12t over t squared plus 2 raised to the third power. So that's going to be 12 times 4 is 48. That's 4800 t over t squared plus 2 to the third power. Now I'm going to want to type that in so that I can evaluate it all these different t values. So numerator is 4800, and I'm going to use x instead of t, divided by denominator, open parentheses for my denominator, open parentheses for my base, t squared plus 2, close parentheses for my base, raised to the third power, arrow out of my exponent, close parentheses for my denominator, a second table because I already have my table settings set to ask, and when t equals 0, we're going to have a growth rate of 0. That makes sense. When t equals to 1, and this is 1 day, is what t is measured in days. So we have, I think that we're going to have to round this to the nearest whole bacteria, I think. So I think we're going to have to call this 178. Let me check. Let's see, can't look, but that would make sense because we can't have a fraction of a bacteria, but if you want to round it, let's see. It doesn't tell us how to round it, so I'll round it to the nearest whole bacteria. C, when t equals to 2, so I get 44.4. That. And then for D is when t equals to 3. We have 10.8189, so on and so forth. So let's just call that 10.8 for dn dt. And E is t equals to 4. dn dt is approximately 3.3. Okay. And so we see that as far as what can we conclude, that we get this idea that it is increasing at a decreasing rate after quickly taking off here, that it's going to do something like this for its should be what the graph looks like. And let's go back and see what the graph actually looks like. For 400 times 1 minus alpha y equals fraction 3 denominator of x squared plus 2 quantity squared. Close that parenthesis. Let's look at this graph. And we want let's make our window go from 0 on x to at least 5 by 1s. And let's go from 0 to maybe shouldn't get bigger than 400 here. Let's go by 20s. Okay, so it's not actually decreasing. I drew that wrong, but it's going up, and then it's kind of leveling off. It's still increasing, but at a decreasing rate here. So we start off completely horizontal, we quickly grow, and then we start growing at a decreasing rate. So there we go. Let's look at one more, and that would be number 71, which is about depreciation. So we have the value V of a machine T years after it is purchased is inversely proportional to the square root of T plus 1. So the value is inversely proportional to the square root of T plus 1. The initial value of the machine is $10,000. So that's going to be K. So V of T is $10,000 over square root of T plus 1. Write V as a function of T, and then find the rates of depreciation when T is 1 and T is 3. So we did the first part already. We wrote V as a function of T, and now we want to find V prime of T. Let's write this as 10,000 times T plus 1 to the negative 1/2. So when I take the derivative here, that's going to be a negative 5,000 T plus 1 to the negative 3/2 times 1 is a negative 5,000 over T plus 1 to the 3/2. So we want V prime of 1 is going to be negative 5,000 over 2 to the 3/2. Negative 5,000 divided by 2 raised to the 3/2. And I get that that's about negative 1,767.77 dollars per T is measured in probably in years. So then v prime of 3 is equal to negative 5,000 over 3 plus 1 is 4 to the 3 halves. Well, that's negative 5,000 over 2 to the third is 8. So negative 5,000 divided by 8 is negative $625 per year at that point. Again, assuming T is in years because we're talking about depreciation, which happens over a long time, that these are probably years, not months or days. The value of the machine is lost over several years of usage, probably. All right, so that's it for this video, and that is also it for this section. And we'll come back next time and start talking about our topics from 2.6. See you for the next video.